Hello everyone. In this video I wanted to give you some insight into the different types of friction that you encounter. Frictional forces are unavoidable in our everyday lives. They literally are everywhere. If we couldn't counteract them, then everything would grind to a halt and nothing could move. On the other hand, if we lived in a world where there was no friction, we wouldn't be able to walk or ride a bicycle. Sometimes the effects of friction are very small compared to the other forces that are acting on it, and we ignore them. Sometimes we ignore them just to simplify the situation, and we assume that friction is negligible. Friction depends on many factors, and it turns out that frictional forces can behave very differently depending on the normal force, and also the nature of the surfaces that are in contact. It's not always obvious when looking at surfaces whether the friction force will be large or small. Sometimes smooth surfaces have greater frictional forces than rough ones. Understanding the relationship between frictional forces and atomic and molecular interactions is actually a very active field of research in both physics and engineering. These relationships are not completely understood. Where Newton's laws are usually held pretty high up as far as their ability to give accurate predictions, the characteristics of frictions that we will describe are valid for only common types of interacting surfaces. So what does that mean? The friction equations that I'm going to present are useful approximations, and they don't apply to all situations. Imagine that you give this crate a quick push and send it sliding across a level horizontal surface. As you might expect, this crate would slow down and then stop. What does this tell us about the nature of the interaction between the crate and this horizontal surface? The object is moving, and then it's not, so therefore there must have been an acceleration. This acceleration has to be parallel to the surface and in the direction opposite the book's velocity. We have no reason to believe that Newton's second law is invalid in this situation. So F equals ma can be applied here. And since we know that the acceleration and the net force have to be in the same direction, this force here, the frictional force, must be responsible for the acceleration of the object. In watching this crate that started with initial velocity and then comes to a stop, and assuming that the acceleration is constant, we say that this object is experiencing a kinetic force of friction. The word kinetic indicates to us that there needs to be movement relative to the surfaces. If you've heard the word kinetic energy, that means energy of motion. So what might the kinetic frictional force depend upon? Well, the two that I'm going to highlight are the normal force N, and I'm under the assumption at the moment that this is a horizontal surface. So if we know the weight of the object, which would be given by its mass multiplied by the acceleration due to gravity, assuming it's a horizontal surface, the normal force must be equal to the weight of the object. So, in a sense, if in fact we know the weight of the object, the greater the normal force will be, and thus the greater the force of friction has to be. This is not always the case, however. If we place this object on a ramp and incline it, the normal force will actually change. However, the weight of the object does not. So it is important to note that the force of friction, kinetic friction, is related to the normal force and not to the weight. It just happens to be a special case where it's flat, horizontal, that the normal force equals the weight. The other factor is this mu value here, which is a Greek symbol, and that's how it's pronounced, as mu, and is referred to as the coefficient of kinetic friction. This is a dimensionless number, and it's determined experimentally. And what it depends upon is the properties of both objects as they go past each other. So if we go back to the crate, sliding on this friction, we would find that there would be a coefficient of a particular value between wood and this concrete slab, if you will. And from that, we could then change this to a wood floor and a wood crate, and we would find that there'd be a different coefficient of kinetic friction. And hopefully intrinsically that kind of makes some sense. It probably is easier to push objects across certain surfaces rather than other ones. I'm sure you've had a much easier time pushing a refrigerator across a tile floor versus trying to push it against a carpet, for example. Something that's a little bit rougher and grabs on a little bit more. As it turns out, this coefficient of kinetic friction doesn't depend upon the speed that the object is traveling. Going back to the crate example, once it comes to rest, it's a good question to ask whether or not friction continues to act on the object once it stops sliding. The answer to this question is more complicated than a simply yes or no. So let's start out by just imagining a sofa here and a person trying to move the sofa. And you push on the sofa, but it doesn't move. Unless you believe that Newton's second law is invalid, then you have to assume that there's some other force acting on the sofa that is counteracting the application of the pushing force. That is to say that there must be a force in the opposite direction that is exactly equal in magnitude to the push of the force. We call this opposing force a static friction force. The word static is used to signify that the object is not moving relative to the surface. Now imagine that you push harder on this couch, and it still doesn't move. Apparently, this frictional force can change in magnitude. And if you stop pushing the box, or the sofa, pardon me, then the force of friction must disappear. How do we know this? Because if you removed the push force, the static friction force has to disappear as well. You need a net force of 0 right at the moment. It doesn't accelerate. So the static friction force is a strange force that changes magnitude in response to other forces. So how do we come up with an equation for this? This is a little trickier. We do have something referred to as the coefficient of static friction, and much like the coefficient of kinetic friction, this is usually experimentally determined. The normal force is also important here as well, but this really needs to be thought of as kind of a maximum value that the force of static friction can be, and not necessarily the force of static friction all the time. So really, in trying to get something moving, we have two different regions that we have to discuss. The static region, in other words, getting the object to move, and then a kinetic region. And to make this even more interesting, the static frictional force usually is larger than the kinetic frictional force. When you look up in books for the coefficients of kinetic friction and the coefficients of static friction, what you find is that the coefficients of static friction usually larger. Now keep in mind that's the maximum value. The frictional force can actually be anything in between this maximum value and 0. Kinetic, however, sits there and is usually a little bit less. And what that would tell us is that it's actually easier to keep pushing something, like a heavy object like a couch across a carpet, once it is moving. It's actually more difficult to get it going, and then once we get it going, it becomes a lot easier. This is also why anti-lock brakes are used in cars. You don't want the cars to slip. You don't want them to slide across the surface. You don't want to be in this kinetic region. You want to remain in the static region because you can actually get more frictional force and thus slow the car down more rapidly. I hope this gave you some insight. Thanks for watching.